So question?
Yeah, sure.
For things?
Going okay. Kind of busy this week, but always feeling busy. Getting almost everything done. Just one more homework assignment tonight, and then I should clear up the rest of the week a little bit.
Okay. Yeah, this semester you have been busy, right? That's what he said.
Yeah, it's just it's about the same number of classes, but all of them the homework takes a little bit longer for all of them than they have in the past. So it's been a little bit more time consuming than previous semesters.
Got it. Just because it is advanced classes?
Um, I would say probably, and then with the Elks trying to open back up and find help and stuff over there, it's kind of like anytime we don't have a worker, I'm the person that gets called, so I have to go either figure it out or do it myself. So it takes a lot of my time also.
Yeah, I can imagine that. Oh, Jeremy?
Hello.
Okay. So I did post the homework. So homework 9. Okay. Okay, let's see how far we can go today. We started constructing or we posed the problem last time. Let me go over that again. Okay. So first of all, what we did was that, so static, so let's say electric potential due to a static point charge, static. Is given by phi of r. R is the observation point, and that's equal to 1 over 4 pi epsilon naught. If r prime is your point at which the charge is sitting, then we have, let me write this explicitly, it is r minus r prime, of course, but this is x minus x prime plus y minus y prime square plus z minus z. That's what we have been working with, or you've seen this for quite some time now. We want to talk about our last class. We derived that the electric potential due to a moving or dynamic, also moving, let's say, it's no more static, moving point charge is is given by RT now. We just barely showed what it is, so let's derive that in a minute. So this will be equal to 1/4 pi epsilon naught in the front. And there will be three space integrals, so it is x prime, y prime, and z prime. Which was there in this case also, it's after the integral that comes out there. And now this time there is a time integral also. Our Green's function was for a particular instant in time, so we had to add up all the contributions from time because at an observation point t, we could get contributions from all over in the past. And that's equal to q times, let me first say this is x minus x prime square plus y minus y prime square plus z minus z prime square. And now we have a new delta function. So first of all, we have this q of derivative cube, or explicitly say this, x minus x prime, delta y minus y prime, delta z minus z prime. That's all charge distribution, so let me put that in a box. So this is charge density of prime q prime. And we also have a delta function here, that's t minus t prime. Oh, can you guys see it? Probably not. I'll change the camera. So it's t minus t prime minus r prime, which is again x squared plus y squared, right? I want to write that explicitly, r minus r prime. So this is x squared, x minus x prime squared, plus y minus y prime squared, plus z minus z prime squared, over c. Is that clear how I get this? Like based on last class, like I've explicitly written it. So it seems very overwhelming, but that's what it is. And this is the simplest case. Is that very clear? Should I go over the steps by any chance? Jeremy? You're good? Okay. Okay, so if we were to evaluate these three integrals, let's do that immediately. We get, so that's equal to, please, back. This is q over 4 pi epsilon naught. X, y prime and z prime can be done immediately, so that's minus infinity to plus infinity dt prime. And oh, I have to specify the problem at this point, right? I think we said this last time. What we're doing is that we're talking about a positive charge moving with a velocity v in the z direction. So its position will be vector r will be just v times t in the k direction or in the z hat direction, and the velocity will be simply v in the k direction. Since we are having the charge density z prime will be vt here. So this is v times t and v times t prime, and this will be v times t prime. Wherever you see z prime, you have to replace it with v times t prime. Okay. Hopefully I didn't confuse too much. Okay, so what that means is that all the replace all the x primes with, oh, again messed up. Okay, I think I made mistakes here, so let me start over. Okay, so I think it's trivial mistakes, but instead of confusing, let me just phrase the problem better. Okay. Okay, so that's your, remember that what we calculated last time is that the Green's function for point charge is this r minus r prime, comma t minus t prime was equal to 1 over 4 pi epsilon naught. Pretty much the same, but I don't want any confusions, so just rewriting it. So this is r, there's no epsilon there. So this is t minus t prime, r minus r prime over c. And that's what it is. So we are talking about a point charge which is moving with velocity v in the z direction. So we said position r is equal to vt, so r prime will be equal to vt prime times k hat. Velocity v prime will be equal to v itself times k hat. What about the charge density as a function of r prime and t prime? That will be equal to q times. Typically, we just have delta function of r minus r prime. This is r prime minus the position of the charge, right? So this is position of the charge as a function of time. So this is position of charge, which is what this is, right? Position of charge. Where is the charge sitting there, right? So that's equal to q times delta of x prime, delta of y prime, and when it comes to z prime, it is equal to minus vt prime. That's the position where the charge is at any point. So that makes it more clear. And from that point on, we have to get our potential. So let's write the expression for the potential. Electric potential due to a point charge, moving point charge at time t will be equal to integrate over all position, this is a superposition principle, but now we have to integrate over time also. That's the only difference. So this is minus infinity to plus infinity dt prime. So dynamics involves take care of all the times also. So this is rho of r prime comma t prime divided by r minus r prime. But remember, our Green's function has a new term in there, and that's the delta function of t minus t prime minus of r minus r prime over c. Let me put this more explicitly. That's what I was writing it earlier, but I think I was jumping steps there. So I wanted to do this again. So this is 4 pi epsilon naught minus infinity to plus infinity dx prime minus infinity to plus infinity dy prime c prime, and finally time t prime. And there are 4 delta functions here because 3 coming from the charge density and 1 delta function coming from the potential itself. So there's a q there. I'll put it in the front q, and there is a delta of x prime, delta of y prime, delta of z prime minus vt prime, and multiplied by this delta function which involves, I'll write that in a minute. But denominator here is x minus x prime square plus y minus y prime square plus z minus z prime square root of that. And the same square root shows up here also. Hopefully it's not too far. Okay. The same square root shows up because there is r minus r prime, so it's x minus x prime square plus y minus y prime square plus z minus z prime. Right, hopefully that's clear. And that's what I was trying to write immediately, but then I think I made some small trivial mistakes which could be confusing. Okay, at this point, do the x prime, y prime, z prime integral. It's much more clear where things have to go. Integrals, delta function integrals are replace x prime with 0, y prime with 0. This is q over 4 pi epsilon naught. There's only t prime remaining after I do the 3 integrals in position. I can do the t prime integral also first, which sometimes we will use, but at this point, let's do the x prime, b prime, z prime. So that's equivalent to, so all these 3 will replace z prime with vt prime. That's the main thing that's happening. And you have t minus t prime minus 1 over c times square root of x squared plus y squared plus z minus v. Z prime gets replaced with t prime. Sorry, z prime gets replaced with v times t divided by x squared plus y squared plus z minus vt prime. That's your expression. And it might notice that we are integrating over all time, right? So what is happening here is that, so this is your observation point. So the positive charge is going from coming from the past and going there. And if you want to measure your electric potential here, when it is very far, its signal will take a lot of time. And when it is very close here, it will take lesser amount of time. And the way we are integrating, it seems like we are also allowing the signal to come from the future, right? Because t prime could be greater than t. T is your observation point. And I am allowing t prime to go all the way to plus infinity. So it seems like signal from the future after it has gone is actually contributing to here. And that shouldn't happen. And that doesn't happen because this delta function, even though this integral is all the way from minus infinity to plus infinity, this delta function actually gets contribution only when t is minus, whenever t minus some quantity. So that makes sure that it is causal. Like we have actually picked the solution which is causal. When we said that this is the Green's function that contributes to it. So the time will always be in the future of t prime. Right? T will always be greater than that. So that should be made clear. And now still it seems like how many solutions does it have? So whenever this delta function goes to 0, this will click, like this is like a counter, and whenever this goes to 0, for whatever time this goes to 0, you get a click, you get a signal, oh, that is this contribution to this field from whenever that distance was. And it seems like there might be more solution. How are we so sure? So let's investigate that, right? But before that, let's take some simple limits here, right? So what happens when, how can you get the static limit from here? So let's do one particular situation. So let's consider the limit c tends to infinity. Or let's make it slow, right? Static has to do with slow, right? So, let's first do c tends to infinity. And remember, c tends to infinity means the signal goes at a very fast pace. So it instantaneously reaches. So that is, imagine you are observing and the charge is going. So what do you expect for c tends to infinity? First thing is that this immediately 1 over c is 0, right? So this is this is called the action at a distance. So immediately it passes on. So that's 0. So let's see what happens here. That's q over 4 pi epsilon naught minus infinity to plus infinity dt prime, and that's t minus t prime. And that's your x squared plus y squared plus z minus vt squared. And what is that equal to? So that's the same as that integral can be done right now. T prime, just replace it with t. So that's the same as q over 4 pi epsilon naught. So that's the same as the old contribution, except that you change your t prime. Actually, this was t prime, right? So I should have been t prime. Except you replace your t prime with t. Like that's how Newton would have, like if you're very far away, when the speed of light really is not significant, it is actually equal to infinity. So this is the same as your old potential, except you change your position whenever your time is there. So z is translationally changing with vt, which is not very hard to imagine. Right? That's the naive way you would see how the charge changes. But the finite speed of light changes this to a more complicated object, which is what we will see today, how the electric potential will look like when the speed of light is finite, and it will be much more complicated, and we will have some simple interpretations, especially for the electric field. We will not reach the electric field today. We will finish the electric potential, hopefully. That's your speed of c tends to infinity, but now let's do the opposite limit, which is more interesting, which is the static case, correct? What if I were to take, starting from here, I take v tends to 0. V is very small, that means to say you go to static limit. So in that case, all this t prime term will actually go to 0, and what we get is q over 4 pi epsilon naught. Again, we have the time integral dt prime. All the velocity v, you set it to 0, so that's t minus t prime. Once the t velocity term goes to 0, what is remaining is just r over c. and that's divided by R itself, which is basically x squared plus y squared plus z squared, right? R. But now this has become time independent. Right? So this is equal to q over 4 pi epsilon naught 1 over r, and that's minus infinity to plus infinity dt prime delta of t minus t prime minus r over c. And what will that integral be equal to? That's a delta function integral at some time t minus r over c equal to t prime that will contribute, but whatever that is equal to 1. Doesn't matter at what time it is contributing, that is equal to 1, and that's q over 4 pi epsilon r, which is the static limit. So static limit is got by taking the v tends to 0 limit, and the c tends to infinity limit. That is the trivial nature where if you had not invoked Einstein, that is how electromagnetism will look like. And now we want to actually look for how things look like in the general scenario. So in the general case, we have to evaluate that delta function. Basically, we have to ask, when does that delta function go to 0? So it involves the quantity. So delta function of t minus t prime is 1 over c x squared plus y squared plus z minus vt prime. So we are asked, when does this go to 0? Right? So how do we do such a problem? Notice that if there was t prime appearing only here, then it was easy because that would have contributed only one place. It is linear, we know when it is 0. But this is like a function. So let me define as a function f of t prime, which is t minus t prime minus 1 over c square root of x squared plus y squared plus z minus vt prime. And we are interested in doing an integral of this kind. So we are doing minus infinity to plus infinity dt prime. And there is some quantity that is t prime dependent. So let me say that's f of t prime or g of t prime. And I have a delta function of a function inside it. And we haven't come across that before. Like all the time when we work with delta functions, we say x equal to something, y equal to something, and this is a complete function in there. And how you do this is equal to, so this is an identity I am giving. This can be proved, but the proof does depend on the geometric picture or geometric analysis of how a delta function works. But without going into those details, I'll give you the identity is that this will contribute at, first of all, you have to find, so the procedure is first find the roots of this equation. So because you have to ask, when does this go to 0? Whenever this goes to 0, it will contribute. You ask, when does this go to 0? That's usually a polynomial equation. Sometimes it could even be having many infinite solutions. Let's say TR are the roots. TR are the roots of the above equation, where R could be 1, 2, 3, how many roots it has. Then this is equal to, for each root, it will get a contribution. So for each root, so let me not, since we don't know how many roots there are, so I just say summation over R. If there are 3, it will go from 1 to 3. Evaluate this at T of R. That's what normal delta function does, right? You evaluate it at that function. Or actually, let me write this in this form. Yeah, so the summation is there, sorry. So this is T of R. And there is 1 over, take the partial derivative of the function f with respect to t prime, and then evaluate it at t prime is equal to t of r. But then you have to take the magnitude of that. Notice what this means. Take the derivative of this argument of the delta function, then evaluate it at the root t of r, and then they take the whole magnitude. That is, say by any chance, if it is negative, get rid of the negative, and then evaluate the normal delta function. So that's minus infinity to plus infinity dt prime g of t prime delta function of t prime minus t of r. Hopefully that's here. This is a standard normal delta function. Oh, am I in the view? Yes, hopefully. Oh, that's not completely visible. Yeah, this is evaluated at t prime equal to t of r, which is the same as once you evaluate this, you simply get t of r, right? So this is g of t of r. Okay. This is often written as an identity. You would write this as. So in your homework, I ask you evaluate this delta function. Like I use the language evaluate this delta function. That means I want you guys to write the right hand side. So this is R. I want you guys to write the right hand side. So basically find the roots, get the derivatives, and this is t prime minus t of r over. Let me do an example so that it clarifies what we're doing here. So example is, let us say we have delta function of, let's say, 2, 3. So this is x squared minus 5 of x plus 6. Correct. So I want to see what this is equal to. So immediately I say, okay, I want to find the equation, roots of this equation, x squared minus 5 of x plus 6 is equal to 0. What are the roots? This x is equal to, so this will be x of r, right? X of r is equal to either plus 2 or plus 3. And then we want to find the derivative. So this is f of x. So what's the derivative of f with respect to x? So this is equal to 2 of x minus 5. So our identity says that go from r is equal to 1 to 2 delta of x minus 2. This is the r x equal to 2, and then take the derivative. So this is 2x minus 5. Evaluate this at x equal to 2, and then take the magnitude. Oh, so this is the first term, so I've already evaluated that, so I don't want to do that. The second one is delta of x minus 3 divided by 2x minus 5 evaluated at x equal to 3, and then take the magnitude. What does that give you? This is delta of x minus 2. 2x minus 5 evaluated at x equal to 2, so that's 4 minus 5, that is minus 1 magnitude of that, plus delta of x minus 3, 2 into x 6 minus 5, so that's plus 1 magnitude, which is the same as delta of x minus 2 plus delta of x minus 3. So there are two delta functions, so that the delta function of a quadratic equation is the sum of two delta functions. Any questions there? I give you a little harder in your homework problem. I ask you to do this for a cubic equation. So find the roots of a cubic equation. Typically, if you're not familiar with the cubic solutions, check like by substitution. Either I give simple ones, either +1, -1, or 0. Probably one of those is a solution. So check whether straightforward solutions of that, and divide it out, and you get the answer. Any confusion there? Because there are homework problems related to that. And I also ask, since this is relatively straightforward, I typically ask this in the exam also. Okay, any questions there? Okay, so that's the simple part. But now we want to do this for an explicit expression which doesn't involve any numbers. So we would like to find out what is delta function related to f of t prime, where f of t prime is equal to t minus t prime is 1 over c square root of x squared plus y squared plus z minus vt prime. So we have to set this to 0. If you want to set this to 0, that means t minus t prime. So if you want to set this to 0, so that's t minus t prime square is equal to 1 over c square times x square plus y square plus z minus vt prime square. And whenever this becomes 0, so f of t prime equal to 0, that's t of r, right? So let's not write t prime, so let's start writing t of r. So this is the root now. Only when it is the root, it satisfies that equation, right? So we immediately have t of r. Let's write this as a quadratic equation in t of r, expand this out. So it is t squared plus t of r squared minus 2 times t of r is equal to x squared plus y squared over c squared plus the z squared over c squared, and then there is plus v squared over c squared times t of r squared, squaring these quantities, and then finally minus 2 times v over c, z over c times t of r. How to write this as a quadratic equation in t of r, or at least we notice that this is a quadratic equation. So that means there will be two roots, right? So this seems to contribute at 2 times. I get 2 distinct times it is going to contribute, but we are going to show that one of them is from the future. And we'll say, oh, that's not allowed, right? We cannot allow a signal from the future to affect today. So we will explicitly, manually not let it contribute. So T of R here is the coefficients of this. So this is T of R square. So that takes care of these 2 terms. Then there are factors. T of R gets contributions 2 places. So that's minus 2 T of R. And that's T That's this quantity. When this moves to the left, it becomes a plus, but I have taken the negative out, so this is minus of V over C and Z over C. It looks odd combination of factors, but we will see that there is some interpret. Remember the gamma, right? There's so many things happening in the Lorentz transformation. So these two go away, and finally there is plus t squared minus z squared over c squared minus x squared plus y squared plus c squared. So that's your A, that's your B, that's your C in the quadratic equation if you want. The solution for this is P of R is equal to negative of this quantity. There's a factor of 2 there, so that means whenever I write this, the factor of 2 in that quadratic equation all cancel out. So that's T minus V over C, Z over C, plus or minus two solutions, square root of T squared and minus 4AC, right? But 4 cancels out the one from the denominator. So that's minus 4 is not set AC, so that's 1 minus V squared C squared times V squared. Too much of algebra, but that's what it is. And again, this is one of the simplest problems, right? This is a charge moving with constant velocity. And imagine if it is accelerating, this gets more complicated. So this is 1 minus V squared over C squared. Okay, let's simplify this a little so that it helps to understand or this algebra. If you do this in the right way, that there is a slight ease in the number of steps that you go about. Let's simplify the quantity inside the square root in a particular way so that we can interpret it as what it is under the for the scalar potential. So it can be written almost having a shape of what is there in the scalar potential. If you're just asking, oh, maybe I should tell that before I proceed. Yeah, so this seems like there is two solutions here, right? Plus and minus, and how do we know which one is which? Does it satisfy in both cases or not? So let's set v equal to 0. We know that when velocity is equal to 0, the static case, we know what the solution is, right? So which solution is actually contributing in that case? So let's set v equal to 0 just for simplicity. So let's set v equal to 0. So T of R becomes, T of R in that case is T plus or minus v is 0, so this is T squared minus velocity is 0, so this is gone. So this is T minus R over T squared minus R over C. T squared minus R squared over C squared, which is the same as T plus or minus R over C. But in the velocity equal to 0 case, we know that we cannot, in the static case, there is no future coming and helping, disturbing the charge. So this has to be minus, right? So we know that this is a negative solution. Right? So the positive solution is dropped from this point. We argue that positive solution violates causality And that we want to respect just because we don't see that all around us that everything is called. So there we are actually dropping a term. So we are interested in the positive term. And then let's look at the, before we finish, we'll have to continue this next time. Or actually no, let me not take extra time, so I'll finish. Okay, so let's process this a little bit. So the square root term, if you allow me, so, and the square of that, so I'll write that as the square of the square root term. That's what that means, whatever is underneath that square root term. So let's expand that out. So it's t squared plus v squared over c squared times z squared over c squared. And then there is a cross term, right? So 2 times t v over c times z over c. And there are more terms in there. So that's minus of 1 minus v squared over c squared times t squared. And there is 1 minus c squared over c squared plus. So plus 1 times z squared over c squared. And finally, that is plus let's cancel things out. So notice there is a t squared here. This term here cancels this term. T squared, 1 times t squared is a minus sign coming in there. This term is plus v squared over c squared. This is minus, so this term also cancels. So that's gone. And what is remaining? So I achieve 3 terms remaining. So this is 1 minus v squared over c squared times x squared plus y squared over c squared. And whatever is remaining, let me collect them together. So that's minus t squared. No, not minus t squared, right? Plus v squared over this one. So plus v squared over c squared times t squared. Or let me write it the following way. So this is z squared over c squared. That's this term. Then there is minus 2 times z over c times vt over c. That's this. And we have plus v squared, t squared, which is vt over c squared. That's a whole square, right? So that's equal to this can be written as z minus vt, the whole square, over c squared. Notice the factor of gamma showing up. So this has this Lorentz feature, right? Notice that what Lorentz transformation does is that whatever is in the direction of movement, it contracts, and whatever is in the perpendicular direction, it doesn't contract, right? That's what Lorentz transformation happens, and the time is also dilated. The time is dilated, the distance is contracted by the Lorentz transformation. And see, this is a factor of gamma here, 1 over gamma squared. It's affecting x and square, x and y, but not affecting z and t. So that's some feature that's showing up. But what is your retarded time? Let me write that down, and then we'll come back. So retarded time then is equal to t minus v over c times Z over C plus or minus, oh, sorry, minus, right? No more plus because we dropped that for causal reasons. And let me write this as 1 minus V squared over C squared. And whatever structure we are seeing here, this will stay. It cannot be simplified further than this because Lorentz transformation treats the direction of velocity differently from other directions. It's divided by 1 minus V squared. One more thing I will do and stop, and that is that, oops, it's TF1. I'll rewrite this in a certain form. I'll multiply this out and rewrite this as T minus V over C times Z over C. There's an identity we get plus 1 minus V squared, sorry, minus, right? So I want to take it on the other side, times the retarded time. So this R, even though we labeled it as the root of that, so it serves to write this as a retarded time. So that's equal to 1 minus V squared over C squared, X squared plus Y squared. Actually, if you notice the denominator in your potential, that has this structure right away. When you actually evaluate it, it will come out and have the structure immediately. And it's just few steps to get the electric potential for a moving charge. And again, notice it seems like it is so overwhelmingly algebraic. There is no symmetry in here, but it shouldn't be there because the direction of motion has some preference or behaves differently from the directions that are perpendicular to them. And we will explicitly see what the electric field is. There's a nice little interpretation in there, and it will all explicitly come out. But these complications will not go away, like the algebraic mess that you see. It won't go away. But then you're doing relativistic particle motion. So I'll stop here and continue from there. So this will have to go to the next class also. And we will also finish the electric field, how they will transform. Okay, thank you.
Thank you.
Thanks.
Have a nice day.
Thanks.